Hi class, welcome to this new video still on diagonalization where we focus on linear independency. Remember what we did in the previous video where we employ some theorem to support your argument how to prove that a square matrix is diagonalizable. One of the theorem was that an n times n matrix A with distinct eigenvalue lambda will be diagonalizable and therefore will generate a set of n linear independent vectors. All right, let's then have a look on these two theorem which fall in line with what we saw before. And the first theorem says that an m times n matrix A is diagonalizable if and only if the matrix A has n linear independent eigenvectors. Also, if eigenvectors v1, v2, vn corresponding to distinct eigenvalue lambda 1, lambda 2 until lambda n of an m times n matrix, therefore the set vn, v2 until vn is a linear independent set of eigenvectors. So from here we can give some propositions. The first proposition is that if a square matrix m times n has repeated eigenvalues that are not defective, meaning that the geometric multiplicity is equal to the algebraic multiplicity, therefore the matrix, there will be a set of linear independent eigenvectors belonging to the square matrix. And in proposition 2, we can propose that if therefore a square matrix having a repeated eigenvalue with multiplicity m, if the multiplicity of the eigenvalue is greater than the multiplicity of the eigenvectors, therefore there will not be a set of linear independent eigenvectors of that square matrix. What we're saying, like for the first proposition, we have that the multiplicity of the eigenvalue should be equal to the multiplicity of the eigenvectors. That is, algebraic multiplicity should be equal to geometric multiplicity. Therefore, we will have a set of linear independent eigenvectors. And here, if the geometric multiplicity is strictly less than the algebraic multiplicity, therefore there will not exist a set of linear independent vector of the square matrix. Let's look on this example. Now, the question is, are there linear independent eigenvectors of matrix B? Let's have a look. B is 2, 0, 0, 4, 2, 0, 6, 2, 4. Now, how do you answer this question? Quickly realize what we did before and use what we explained in previous video. The first step is to solve the determinant of a minus lambda I equals to 0, right? Which is finding the eigen value. But what do we observe in this matrix B? We observe that this is a triangular matrix. Therefore, what it gives is that the eigenvalue of this matrix will be the element of the diagonal of matrix B. Like this, the eigenvalue will be lambda 1 equals to 2, lambda 2 equals to 2, and lambda 3 equals to 4. So what do we see here? We see here that lambda 1, so we have a repeated value of lambda, of the eigenvalue. So we have lambda 1 equals to 2 with multiplicity 2. This we call algebraic multiplicity 2. And then we have the other value, which is 4. Now, let's find the eigenvector for lambda 1 equals to 2. We have to solve the equation a minus lambda 1I v1 equals to 0, which gives me that I'll have 2 minus 2, 0, 0, 4, 2 minus 2, 0, 6, 2, 4 minus 2, putting it in the form of row echelon, and this will give me 0, 0, 0, 4, 0, 0, 6, 2, 2. Yeah, so I can write row 3 equals to row 3 minus row 2, and then next I'll divide row 2 by 2, and then divide row 1 by 4. This will lead to 0, 1, 3 over 2, 0, 0, 1, 0, 0, 0, right? And from here I can notice that I have here from this equation, I can see that x1 is free, and x2 as well, and then I only have that x3 is, sorry, x3 is fixed, yes, and I have that x2 is free and x2 is fixed. So this will give me that x1 equals to t, and x2 equals to x3 equals to s. But from the first row, what do I have from the first row? From the first row, I have that x2 equals to minus 2s, which is s3, and then from the second row, I have that s3 equals to 0. So this gives me that my first vector, therefore, which is x1, x2, x3, will be equals to t x2, right? So it gives me that x2 equals to 0, 0, and x3 equals to 0. So I have t1, 0, 0 with t any scalar. So what do we see here? We quickly realize here that the eigenspace of lambda equals to 2 of matrix B, okay, generates one eigenvector. One eigenvector 1, 0, 0. What do you realize here? You realize that the geometric multiplicity, which is the number of eigenvector in the eigenspace, so the geometric multiplicity is less than the algebraic multiplicity. So the algebraic multiplicity is 2, right? And the geometric multiplicity is 1. So you have 1 inferior to 2. And this therefore means that, employing the second proposition, this means that this set, this means that there does not exist a set of linear independent eigenvector of matrix B. Now, I hope you understood what we did in this video, and you can have the other value. You can have, for lambda 2, you can find the other value of the other eigenvector, right? For 4, you can easily have that, and that will give you T511, which is an exercise that you can easily solve out. So in this video, we show you how to answer the question if a square matrix generates a set of linear independent eigenvector. In the next video, you'll be exposed to more practical exercises that will enable you to grasp the content of what we are sharing. Thank you very much.